during this session. It will be followed by Vladimir's concluding remarks at the end. So we'll be 10 minutes behind schedule.
Good morning, everyone. As was pointed out, this is a collaborative talk between myself at the Bell Laboratories and initially the group of Alex Bell at Berkeley. And the affiliations here are still pretty much the same, except for Phil Winslow, who is now at Chevron Research. He was at the time. It says a hand next to it, stops it, or whatever used to. Let me give you some beta of why we want to talk about the NMR in these systems here, and that is the advantage of the carbon-13 NMR in the studies of Fischer-Tropsch synthesis, which I think the chief ones are as follows. First of all, we can do in situ analysis on these materials, and that is we don't have to look at single crystals, we don't have to reduce the pressure or the temperatures in these materials. The things that we're talking about today are static systems as opposed to online reactors, mainly because for the initial studies, we didn't want to put the money into having a carbon-13 CO flowing through as we did the long-term characterization. The NMR can detect all the species pertinent to Fischer-Tropsch reactions, as opposed to other techniques which have different extinction coefficients or detectability of these things. NMR detects equally well carbon monoxide, carbides, the alkyl groups, and the graphite, as I hope to show you later in this talk. More important, as it detects each of these things, it provides straightforward quantitative analysis. You don't have to go off and calibrate extinction coefficients or other materials that are there with unknown samples to try and figure out how much is actually there. And something that's now just being explored, NMR also offers studies of the dynamics of these species, interconversion or this motion on the surface. Now, that was what I was going to say about that, but let me if this is really true, if these things really can say that much, then why hasn't the NMR gone much farther than it has in the years or so since we did these initial studies? The only work that I know of going on in this area is Alex continuing the stuff on his studies at his group at Berkeley. So either these claims are false, either that it really doesn't provide this information, or there's perhaps some other reason. Is it because the NMR is perhaps difficult to get going in one's lab? Is it no one believes these results? Is it the equipment is expensive? Perhaps you could provide some information for me during this talk, and that is as we go through here, and if I'm not explaining it well, or if there's some reason you don't believe what's going on there, I would like to be interrupted, and perhaps we can talk and go into some length about some of the different things I'm going to talk about here. I'm going to take a different approach than perhaps some of the other NMR talks that you've seen. And rather than go into a lot of the techniques of how we used to measure these things, I'm going to try and decompose all the spectra into these fundamental quantities, and that is that every one of these peaks, every peak in every spectroscopy you're going to look at is going to have these different properties. And that is, first of all, there's going to be an intensity to that peak. There's going to be a position to that peak. That is, it's going to be shifted relative to some other thing. And finally, it's going to have some width or dispersion. This is common to all different types of spectroscopy. In NMR, particularly in solids, we just have to remember how do we interpret these things in terms of these physical phenomena. And those physical phenomena that are pertinent to this type of study here are as follows. The intensity is just the amount of nuclear magnetism in the sample, which is directly proportional to the number of nuclei there. We get directly the quantitative analysis. We can also look at how the intensity performs under various pulsed experiments. That gives us information on relaxation. Relaxation can be directly related to various emotional properties. As most of you are familiar from studies in carbon-13 or proton NMR of organic liquids, the position of a line, that is the shift of the line, is typically determined by interactions with electrons. The most common being the chemical shift, that is bonding electrons have this induced angular orbital momentum that are going to shift the line from some known standard, for example, TMS. When you're working with metals, we have another interaction, the electron-nuclear contact shift, also known as the night shift, indicative of being in contact with metals that have, or particles that have a metal band structure. This information provides chemical identification. We're all familiar with that through organic liquids, and the electronic properties of the metal. The information that comes out of the analysis of solids, which is often seen as the real disadvantage of working in solids, is the width of the line. And that is, instead of these being nice, sharp lines you see in organic liquids, there's going to be broadening. Often causes them to overlap, but that broadening carries with it some important information used for identification and characterization. Typically, the orientational anisotropy of the electron interactions and the dipole couplings. And that is, what type of asymmetry is there at this site caused by other dipoles in the area, other nuclei, and the electrons. Let me just elaborate on one of these being the chemical shift. As you recall, there are discrete bands in the carbon-13 NMR spectra corresponding to different types. First of all, I want to point out that we're going to be measuring the frequency shift of the line in parts per million. Okay, it's a fractional shift, so it's independent of what field you're working at, relative to some standard. For carbon-13, that standard is tetramethylcyanate over here. Okay, and I applied it in the standard way that upfield is in this direction, downfield is in this direction. This happens to be on the sigma scale here, so we're going negative over here. You also see the delta scale, which is positive over here. All we need to worry about is that this is higher frequency, this is lower frequency, okay? Two common standards are benzene and carbon disulfide that are here. Now, I've diagrammed the different bands you'd expect to see for different molecules or species in Fischer-Tropsch synthesis. We have the oxygenated species here in red, CO, or other types of acids, oxy groups here. We now have those that are just totally hydrocarbons, double bonded, triple bonded, and single bonds. And we also have those that are somehow involved with the metal. Here, 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 and the traditional carbides. I'll come back to this later when we want to analyze the different species that are there. As a means of introduction of how we produce these samples, I want to steal something from Alex's talk later, and that is that I'm going to introduce a little bit of the transient response technique that we use to prepare these samples with different amounts of carbon on the surface. And what first showed the potential to be able to sort these out was Alex's work with the transient response that showed that we could variably, we could change the type of carbon, type and amount of carbon on the surface in known ways that we could then use to identify with the carbon-13 NMR. Consider the following experiment, where one takes a catalyst at about anywhere from 170 to 200 degrees C. In this case, it's 4.3% ruthenium on silica. Reduce it in deuterium, which is this point over here, and then watch the amount of totally isotopically enriched methane that appears in the effluent as a function of time. Okay, so if one switches over from deuterium, carbon-13 CO plus deuterium, so initial uptake period here, and then a pseudo steady state production of the methane for a short amount of time, about 5 minutes here. Okay? At this time, we rapidly switch from carbon-13 CO to carbon-12 CO. The infrared spectroscopy shows that the oxygenated carbon-13 forms disappear in a very short time, less than a couple seconds. Okay? So those drop off very quickly on the scale here, but we see carbon-13 continue to appear in the product for a time much longer than carbon-13 is there as oxygenated species. Okay, so there's evidence that there's some sort of carbon-13 on the surface that's not bonded to oxygen. More intriguing was the next step, and that is this: if one extends this experiment and following this initial steady state period, and then some titration with this deuterium here, then purges the sample with helium, this converts the carbon on the surface to different forms. If you then resume the titration at some later point, you get a methane, a type of carbon that produces methane very quickly, and the standard methane production over here, approximately equivalent to this production here. The total integrated amount of this peak is somewhat related to, proportional to, let's say, the amount of induction time that one reacts with carbon-13 CO here. The relative ratios of that rapid producing, the C alpha, and the slower producing is proportional to the time that you purge with helium. That is, the longer one purges with helium, in general, the more intense this rapid peak is going to be compared to this less rapid peak here. Okay? Now, to sort this out with the NMR, I'm going to talk about samples that were quenched from this reaction at 3 different locations. The first one being at point A, shortly after the carbon-13 is purged from the sample will be carbon-12. This will represent the steady state structure of the carbon-13 on the surface. Second is after this conversion, so as to convert some of this steady state into some of this highly reactive form. And the third, C, being many, many meters that way, being the titrated samples reacted in deuterium for 2 hours to remove all the reactive carbon off the surface here. A note about this quenching process, it's inevitable that the state of the carbon changes a little bit. We take the reactor, which is at 200 degrees C or so, and bring it down very quickly in temperature. First turn off the flow, then bring it down in temperature, seal it off, and go do the NMR. We've done the studies on this that we can bring this down, let it set for a day or so, bring it back up in temperature, turn on the flow, and exactly resume the this transient response curve that we've seen here before. So we know whatever changes we're making are reversible on these samples, but we aren't sure to what degree the changes are going to be affecting the spectra we see. I think you'll see later from the type of species that we detect, these are not species that are going to readily be converted back and forth by that process. Now, at points A, B, and C, we were first encouraged because indeed the spectra are different. That is, we quench the spectra at different times, so we can actually see differences in the spectra. This is quenched at A, containing mostly the beta form of carbon. You see, it principally has this peak. After we do the conversion, that is the purge with helium, we see in addition to this peak, we form something in this area, the downfield region down here. And finally, after reacting the sample in deuterium for a couple hours, we remove all the reactive species off the surface, leaving us only with this lumplet down here. Okay? First thing you want to notice is that the width of these lines is horrendous compared to high-resolution spectra. That is, most of the isotropic shifts for carbon-13 span from 0 ppm to about 200 ppm. The width of any of these lines totally will overlap every other carbon-13 species that's in there. The initial response would be, well, let's run out and do magic angle spinning because we can resolve all these things and thus have highly non-overlapping lines. That inevitably is a good thing to do, but not in the beginning, because what you're going to do is throw away all the information that's there. What I want to try and point out is that the information about the identification of these lines, the characterization of catalyst, is contained in the widths of these peaks here. Okay? Let's consider first the unreactive carbon on the graphite, or on the, we've given away the punchline there, on the ruthenium on the silicon. Okay? We have this peak. I don't have time to go into it, but these are not two peaks here. This is one single peak that has this very characteristic shape with this low shoulder over here and a higher shoulder over here. What causes that width? Well, let me back up. I forgot to go through the steps. And it's first of all the intensity. The intensity of this tells us that, the integrated intensity tells us the amount of carbon here is proportional to, or not proportional, equals about 1 carbon per 20 rutheniums on the surface. Okay, so we know the approximate coverage of carbon. Second thing is the position of the line. The center of mass of this line is about minus 90 ppm. Okay, knowing it's non-oxygenated, we know that corresponds to something that has double bond character. Okay, but there are many things in that category. What might it be? In order to understand that, what we need to look at now is the width of this line, the characteristic shape of this. And as I pointed out before, the width of the line in this case, is going to be directly related to orientational anisotropy of electron coupling. Other experiments we did, notably looking for couplings to other carbon-13 and to protons, showed that dipolar couplings are not the major contribution to the width of this line. Okay, for sake of time, I'm going to leave that out and just talk about the analysis in terms of this coupling here. All right? In NMR, the characteristic shape of a line caused by an orientational anisotropy is the chemical shift powder pattern, which has a very distinct shape determined by its principal components, the first, second, and third here. Okay? The average of these, of course, equals the center of mass of the line. The relative placement of these is a very strong indicator of the symmetry of that carbon in the sample. And that is the overall width from here to here tells us something about the change in the anisotropy from one orientation to another orientation of the sample. That is, for example, let's look at CO, which has one of the broadest chemical shift powder patterns. And that is for CO in a polycrystalline sample, for those that are oriented with the carbon-oxygen parallel to the external magnetic field, that has one distinct type of shielding. Those that are perpendicular have another distinct type of shielding. Okay? That change in that change in anisotropy between those two causes that broad line. Methyl groups, or CH4 or something, which has no anisotropy, has an infinitely sharp line. Okay? No anisotropy there. That tells us a lot about it that you don't entirely get from the center of mass. So the relative placement of these tells us something about the shielding. So the first thing you do is take that theoretical expression and fit that to the powder pattern, and we find that within the noise, we do have something that goes along well with the shape of a typical powder pattern here. Okay? But you can't then take this fitted powder pattern and calculate what the structure is. We just don't have ab initio techniques to go in that direction. In fact, what you do is go out and look for some compounds that might explain this. Well, unreactive carbon on these samples is probably, as a good guess, graphite. And so we went out and measured the spectrum of graphite, which isn't truly graphite. We're unable to get a spectrum of pure graphite. It's so so good of a conductor, approximately equal to copper in certain dimensions, that it shields the thing and you don't see a spectrum like this. What this is marketed as is called amorphous carbon, but if you look at this with X-ray spectrum, what you find out is it's actually turbostrated graphite, and that it doesn't have registry of the crystal for more than about 100 angstroms or so in any direction, but that's nice because it cuts down on the conductivity enough to give us this spectrum to show here. And we find that the principal components here and here agree well with the unreactive carbon on the surface. Okay. Moreover, this is an extremely unique line shape in that the intense component, this one, is upfield of a less intense component. This happens only for those types of carbon that have most of the bonding in the plane perpendicular to the axis of symmetry. As I pointed out for CO, which has this broad powder pattern, its intense component is over here, the weak one is over here. The bonding is along the axis of symmetry. For graphite, it's exactly the opposite. Okay? So we believe that's graphite on the surface there. We now have a probe quantitative analysis of graphite. Let me proceed to the next part of the talk, which is we're now going to do the reaction, switch over, remove the carbon-15 from the oxygenated species, purge with helium so as to create amount of the alpha carbon, the highly reactive carbon on the surface here. Okay? We're going to get to the alkyls first. What I want to point out is that we're eliminating the other things from the spectra that are not the alkyls. Okay? And here we see that, as I pointed out before, this process converts some of this peak, that's the steady state amount, into these downfield peaks over here. You see somewhat of it being created on the sample ruthenium on silica, but we see enormous peaks for carbon on ruthenium metal. Okay? Well, we can go through here and now integrate under these lines, and we get the approximate intensity for the carbon to ruthenium ratio. On both of these, the ratio is approximately 1 carbon for 5 ruthenium atoms. Okay? It's just coincidence that with other samples you can see other things. Well, what does the center of mass or the line position tell us in this case? If we go back to the chart of isotopic shifts, the relevant ones for the species we might expect here, and we find that it's a somewhat unexpected shift, and that is this chart was drawn up before we did the study, and the center of those lines, minus 390 ppm, is somewhat off the line. This actually does extend down to minus 540 ppm for different types of carbides. Okay. I didn't rule out that it might be something like this, because it just could be that there weren't enough of these things measured to actually explain the shift down to this direction. What we did was go in and look for dipole couplings to the other species that might be bonded here, carbons, carbon, hydrogen, or whatever, and found no such couplings, thus confirming that it's the carbide species. We have a little bit of time, so I'm going to insert an interlude here of what one can do. If one accepts that analysis, one can now go farther in the interpretation of that peak. And that is, the shift of that line is caused by conduction electrons. Pen, Agil, Agi. Pass this one. That is that the conduction electrons in the metal have a discrete effect on a well-known effect on what the shift of this carbon line is going to be. And this is given from the so-called Karinga formula. And that is, there's a relation between the night shift, that is the peak position, and the conduction electron contributions to the spin lattice relaxation time. So we have the shift in the line relative to the resonant frequency, and the spin lattice relaxation time, which are the ratio of the electron and the nucleus, and the temperature, this temperature dependence being key. The way to convert this night shift is to measure the temperature dependence and see this linear relation there. From that, you can then get the information on the density at the Fermi level. That's not the key point. Interesting in itself, though, is that this work I'm now quoting from is that of the group of Slichter and co-workers at Illinois. And sure enough, at lower temperatures, one sees this linear relation extrapolated here to a temperature of 0. What's interesting is that at higher temperatures, this now deviates from this linear relation caused by the Karinga relation. Okay? That's caused by the additional contribution to relaxation from exchange, motion at a site. That is, instead of just sitting at a site and having these flipping electrons coming by and causing relaxation, if the carbon now starts to move between sites and sees that fluctuating field, there's an additional contribution to the relaxation, to this T1, caused by the difference in chemical shift as it changes through the site and the correlation time of the exchange. If we then extract off that extra amount of relaxation from the previous plot that I showed you, extract off the Kringa contribution, what they did in a very clever way was find that contribution that was due just to this chemical exchange. The interesting thing here, if you then assume an Arrhenius behavior, temperature-dependent activation energy, you can extrapolate, you can calculate the activation energy for this, which is 7 kcals per mole. Somewhat of an interesting number because if one goes by the rule of thumb that perhaps it should be some fraction, say a quarter or a half or so of the heat of absorption, which it should be for carbides 100 or 110 kcals per mole. 7 kcals per mole is a number perhaps one wouldn't expect on these samples here. But this is clearly what the data say here. Kind of a surprising number for the motion of carbides on the surface here. Okay, so that was an example of how you can use NMR to characterize the dynamics. Let me proceed now to the tidal species here, and that is the alkyls on the surface. As has been pointed out in a number of other studies, the alkyls dominate on the surface at steady state reactions. We have here the sample now quenched at a short time after steady state reaction so as to remove the carbon-13 from the oxygenated species, leaving now representation of what the surface looks like at steady state. And as I pointed out before, we see this peak that, at least on the scales I've been plotting it here, looks sharp. But clearly it's not sharp. It has a half width of about 50 ppm. And as you recall, separations for lines in high resolution NMR are often fractions of a ppm. All right, so we have a lot of different species hidden under this line here. Okay? First of all, the intensity, of course, tells us how many alkyls are on the surface. It corresponds to about 0.7 carbons per ruthenium on the ruthenium silicate catalyst. Okay? The position of the line tells us something about the identity of that. And that is, the position of that line drawn through over here tells us it's some sort of sp3 carbon, all hydrocarbon, or perhaps something bonded to a metal species. Okay? But besides the width of the line, there's also occasionally evidence that the line is composite. From some later work, collaboration with Alex's group with Grant Yucamizo for carbon-13 on reacting and ruthenium on titanium, we occasionally see a peak splitting here. Now, given the noise, that peak splitting perhaps in itself would not be that significant, except if you try to fit this to a single Lorentzian component, you find that the top doesn't match with the sides here. In fact, you need to fit this with two components to explain the splitting here. Circumstantial evidence, perhaps enough to drive us into more. 5 minutes, okay. I started at 8:45. All right, we're very close. So what's a way we could perhaps differentiate that species? And that is, instead of producing it in deuterium, let's produce it in hydrogen. Because the width of the line for carbon-deuterium couplings is 2.6 kilohertz, whereas carbon-hydrogen coupling, hydrogen being a stronger dipole, has 10.4. So if there's going to be some contribution from the couplings to the hydrogen species, we should see the line broaden. Okay? And sure enough, if you take a sample prepared totally in deuterium, compare that same sample prepared in hydrogen, you see very distinctive change. The base of this species has broadened. And that is not the entire peak broadened, but a portion of that peak broadened. You see that through a different spectrum here. You see a sharp peak disappear and a broad peak come in. Okay? Well, maybe that's a little bit iffy because there were two different samples involved in that. You can remove that dipole coupling in a different way. And that is, we start off with now a different sample, and same type of spectrum I showed you here before. I'm biasing the eye to suggest that there's a superposition of a Lorentzian peak and a broad Gaussian peak here. We can show that the width of this Gaussian peak is due to hydrogen couplings by going in and irradiating the hydrogen spectra, hydrogen nuclei at the same time irradiating the carbon spectra, and we see that peak narrow. Okay? There's a mistake to blow this one up. These two peaks are now the same size, but this peak has become noticeably larger because this broad underlying Gaussian here has become much taller. Okay? One sidelight. We can also do dynamics in a different way here. Rather than looking for the T1 contributions, we can look at the line width contribution. That is, as we cool this line down, this alkyl group, we look at the broadening of this line as a function of temperature. Okay? Which relates exactly to the correlation time for that type of motion. If we then plot 1 over the line width, this approximate correlation time with the inverse temperature, we we find we have a linear region here. Again, assuming an Arrhenius behavior, we can extract an activation energy from this. We get about 0.6 kcals per mole for this type of motion, right? Very fast type of motion. That is something corresponding to more of a physical rearrangement as opposed to a chemical process. Now, one final thing, I'll conclude with two more view graphs, and that is this. I'm going to make an exception here and talk a little bit about the technique of NMR because I think it's warranted. I want to narrow this line down, and I want to reduce it to its residual components. For this, I'm going to use something that's known as magic angle spinning, in which there's very little magic, but just some clever physics. And that is the width of these lines, that is the width, is a function of the orientation of each of these species, theta. And that is, if we have a distribution of theta in our polycrystalline sample, as opposed to just seeing the isotropic shift, we're going to see some broadening, this anisotropy, times this, the second Legendre polynomial. As theta changes, right, we're going to see a distribution of the width over here. But, so that corresponds to each of the principal axes being at some distribution of theta in your sample. Consider the following now. If we take the sample for that particular species and cause it to rotate about this axis, okay? So we cause this vector to move in this circle here, that axis being at theta prime relative to theta, or the rotation axis is this relative to h naught. We can then decompose this from the addition theorem for second harmonics, right, for spherical harmonics, into this component is just the sum of the function in terms of the rotation axis, and compared to here, we find out if we set the rotation axis equal to 54 degrees, this term becomes 0. Therefore, the entire interaction vanishes for every theta prime, okay? Thus the so-called magic angle spinning. We then spin about this axis. We see only the isotropic shifts, orientation of dependence of chemical shift, and dipolar is removed. If we then look at the alkyl peak, I'm now plotting a spectrum that's approximately 20 times the frequency width as I showed you before. Okay, I've blown this up to the detail here. And we're now plotting from 0 ppm over to this region. We find this very broad peak, which had a width of about 50 or so ppm, decomposes into these sharp peaks, and I'm trying to bias your eye by these fittings of these Lorentzian components underneath here. Coincidentally, what was nice is that the isotropic shifts of the methylene groups here in the middle and the terminal methyl groups agree very nicely with what you see for normal alkyls, okay, within 1 ppm, all shifted 1 ppm to downfield for some unknown region. And we can assign this B peak to the methylenes, the E peak over to here. C and D correspond to the length of the B chain here. We get the D's corresponding to those with this being 1 or 2, the C's corresponding to this being the longer chains. The assignment of the A peak is unknown. As we pointed out before, we don't exactly know where carbon should be when they're bonded to the rutheniums. It can be anywhere from 40 ppm down to minus 10 ppm. This line having the broad width suggesting some heterogeneity of the surface that it corresponds well with that assignment. What we can get from here, as I conclude, is that from this you can directly determine the length of the alkyl groups on the surface. And that is, you know the amount of terminal groups here. This is the methyl. Okay? If you then just calculate the length of this one here, you then know the length of your alkyl groups as your sample runs. This was after 5 minutes of calculation. We have an N that's approximately, I think, 4.5 after this short reaction here. Okay? With that, I conclude. Thank you for your attention.
There is space for one question.
Mike, in your experiments, you see the two components, the alkyl groups, and you did it before you did the coupling, and now the other components.
Right.
One of them was an effect. The sharper component didn't appear to be sharpened more by the dipolar, dipolar coupling. Do you think there's two domains of carbon, two different motion domains?
I think there's a continuous domain is what's there. They just happen to divide out nicely into a single Gaussian and Lorentzian when you do the protons there. That's not to say that you couldn't fit it to a continuous distribution of Gaussians and Lorentzians. No, the dipole coupling, that's right. It's not, the dipole coupling is still very efficient. It's just that the motion is even more efficient. It's already removed it through the dipole couplings in. What I did point out was this was just a characterization to assign these different peaks here. We've taken these and tried to follow the chemistry in that. We find that the more mobile, the more narrow peak, is the one that's selectively depleted when you purge this with helium. Coincidentally, purging with helium tends to encourage the formation of the graphite, which would suggest by circumstantial evidence that that more mobile alkyl group is the one that's more of the precursor to the graphite on the sample there. Okay? Circumstantial.
Thank you very much.
Vladimir,
The next.
Can I say something? We